Welcome to Chapter 4, where we explore the fundamental building blocks of matter, atoms and elements. Atoms are the foundation of our sensations. From the silicon and oxygen atoms in seaside rocks to the molecules in the air we breathe, these tiny particles shape the world around us, including the distinct smells of the coastline. Atoms are incredibly small. A single pebble from the shore contains more atoms than you could ever count, far exceeding the total number of pebbles in a bay. To visualize just how small atoms are, imagine if every atom in a single pebble were the size of that pebble. The resulting collection would be larger than Mount Everest. Atoms compose matter, and their properties dictate the nature of the substances we encounter. There are about 91 naturally occurring elements, and consequently, about 91 different kinds of atoms. The idea of the atom dates back to Democritus in the 5th century BCE. He postulated that matter is composed of tiny, indivisible, and indestructible particles he called atomos. Over 2,000 years later, in 1808, John Dalton formalized an atomic theory. His model proposed that elements are made of indestructible atoms, that each element has unique properties, and that atoms combine in simple whole number ratios to form compounds. Modern technology allows us to observe atoms directly. Using a scanning tunneling microscope, scientists have successfully manipulated xenon atoms, confirming the atomic theory through visual evidence. J.J. Thomson's discovery of the electron proved that atoms have internal structure. His plum pudding model suggested that negatively charged electrons were embedded within a sphere of positive charge. Rutherford's famous gold foil experiment in 1909 challenged existing models. By firing alpha particles at thin gold foil, he observed that while most passed through, some were deflected at sharp angles. These results led Rutherford to propose a nuclear model of the atom, where the atom's mass is concentrated in a dense nucleus rather than being spread out as previously thought. Rutherford's theory states that atoms are mostly empty space. A dense, positively charged nucleus contains most of the mass, while negatively charged electrons are dispersed throughout the surrounding volume. The distribution of mass within an atom is highly non-uniform. The nucleus is incredibly dense. If solid matter were composed entirely of nuclei, it would be as dense as the material found in neutron stars. To understand the relative size, consider that a proton is nearly 2,000 times more massive than an electron. If a proton were a baseball, an electron would be no more than a single grain of rice. Finally, electrical charge is a fundamental property. Opposite charges attract, while like charges repel. In a neutral atom, the number of positive protons and negative electrons are balanced, canceling out their charges. Let's look at the subatomic particles. Protons and neutrons share very similar masses, while electrons have negligible mass. This table provides the data needed for your homework. Matter is typically charge neutral. However, in an electrical storm, this balance is disturbed, leading to the rapid, dramatic rebalancing of charge we observe as lightning. Elements are defined by the number of protons in their nucleus, which is called the atomic number, represented by the symbol Z. This number determines the identity of the atom. The periodic table is organized by these atomic numbers, listing all known elements in a structured format. Many chemical symbols are derived from English names, but others originate from Latin, such as quote, kalium for potassium and natrium for sodium. Others, like lead or copper, also have ancient roots. Element names often tell a story. Some reflect properties, like argon, meaning quote, inactive, while others honor countries like Poland, France, or America, or even famous scientists. For instance, curium is named after Marie Curie, honoring her groundbreaking work. Bromine, meanwhile, takes its name from the Greek word for stench, referring to its strong-smelling vapor. Dmitry Mendeleev, a Russian chemistry professor, observed that when elements are arranged by relative mass, their properties recur periodically. This pattern allows us to group elements in vertical columns based on similar properties. Mendeleev's arrangement was the foundation for the modern periodic table. Mendeleev's periodic law summarized observations of his time. While it described these patterns perfectly, we will look to a deeper theory in Chapter 9 to explain why they occur. Elements on the periodic table are broadly classified into three categories: metals, nonmetals, and metalloids. Metals, found on the left, are generally shiny, malleable, ductile, and good conductors of heat and electricity. They often lose electrons during chemical changes. Nonmetals, located on the upper right, have varied properties. They are often poor conductors and tend to gain electrons in chemical reactions. Metalloids, or semimetals, sit along the border between metals and nonmetals. They act as semiconductors, making them essential for modern electronic devices like computers. Finally, we distinguish between main group elements, which follow predictable patterns, and transition elements, where properties are generally less predictable based on position alone. The periodic table organizes elements into specific groups. Key areas include Group 1A, the alkali metals, Group 2A, the alkaline earth metals, Group 7A, the halogens, and Group 8A, the noble gases. Alkali metals, such as lithium, sodium, potassium, rubidium, and cesium, are highly reactive elements found in the first group of the periodic table. Alkaline earth metals include beryllium, magnesium, calcium, strontium, and barium. These elements typically exhibit distinctive reactive properties. The halogens, found in Group 7A, include reactive nonmetals like fluorine, chlorine, bromine, iodine, and astatine. Group 8A consists of the noble gases, including helium, neon, argon, krypton, and xenon, which are known for their relative chemical inertness. In chemical reactions, atoms gain or lose electrons to form charged particles called ions. Positively charged ions are cations, while negatively charged ones are anions. Ion charges are written with the magnitude first, followed by the sign. Cations form when atoms lose electrons. For example, a lithium atom loses one electron to become a positively charged lithium ion, as shown by this charge calculation formula. Conversely, anions form when atoms gain electrons. A fluorine atom gains one electron to become a negatively charged fluoride ion. The charge is again determined by the balance of protons and electrons. For main group elements, the column number indicates the number of valence electrons. Elements tend to gain or lose these electrons to achieve the same valence electron count as the nearest noble gas. This table illustrates how the group number helps predict the charge of an ion. Please note that some elements like silver and zinc have charges that do not follow this group-based pattern. While atoms of the same element always have the same number of protons, the number of neutrons can vary. These variants are called isotopes, and every element has a unique natural abundance of them. Neon is a classic example of isotopes. Naturally occurring neon consists of three isotopes: neon-20, neon-21, and neon-22, which differ solely in their neutron count. Isotopes are represented using a specific notation that includes the mass number as a superscript and the atomic number as a subscript alongside the chemical symbol. The mass number is defined as the sum of protons and neutrons in the nucleus. By subtracting the atomic number from the mass number, you can easily determine the number of neutrons in an isotope. Finally, another way to denote isotopes is by writing the element name or symbol, followed by a hyphen and the mass number, as seen here with these neon examples.